So the next part of differentiation involves higher order derivatives. Okay, so simply when we differentiate something a first time and then potentially a second, third, fourth, however many times is required by the question. Okay, so you just basically take whatever you've got for the first derivative and then differentiate again. Okay, so it's something like this. You start with a function y, the first derivative will be dy by dx, just as normal. Okay, but in terms of how we write the second derivative, it's d squared y by dx squared, right? It's not to be confused with dy by dx all squared. It's going to come in when we do implicit differentiation, so don't get the two of them confused. If we're doing the nth derivative, it would just be d to the power of ny over dx to the power of n, okay? Right, this is quite used quite often in terms of mechanics and things like that. So you might start with a first function that would be the displacement. If you differentiate that, that would allow you to find the velocity at a certain point. And if you differentiate that, then you'll be able to find the acceleration at a certain point. Okay, so it's very useful in a context when we're dealing with mechanics and the dynamics of an object. Okay. So in terms of a couple of straightforward examples, if we're going to find the second derivative, the first thing we need to do is find the first derivative. There's no easy way to go from the function to the second derivative. You have to go through the first derivative, and it's just the same as before. If we've got 5x to the power of 4 is our y, then our dy by dx would be 20x to the power of 3. Okay, as long as it is in differentiable form, then we can go on and find the second derivative, which in this case would just be 60x squared. Okay. For the second one, okay, if it's e to the x, anything e to the x, then it's still just going to be straightforward. You just got to remember apply the chain rule. Okay, so same with all of these differentiations. Look at them first before you start bashing on with differentiation. It could be a case of chain rule, it could be a case of product rule, it could be a case of quotient rule. So establish what you're going to do first, and then make sure you go ahead. And obviously, if it's the second derivative, you might have to do one of those things twice. So if we've got e to the 7x, when we differentiate that, it becomes 7e to the 7x. Okay, we differentiate the index part, we get 7, and we multiply by that part. Okay, in which case, if we differentiate again, the same thing actually applies, and it becomes 49e to the 7x. So in the third one there, we've got x minus 1 to the power of 4 all cube rooted. Okay, so you might want to write it in differentiable form first. In other words, x minus 1 to the power of 4 over 3. Right, ordinarily, and well, this is chain rule, but obviously when we actually differentiate what's in brackets, we just get 1 anyway. But look out for the situation when you have something like 2x minus 1. Okay, so 2x minus 1, we'd differentiate what's in the bracket, and we'd get 2, in which case we'd have to multiply by that 2. Here it's not going to have an effect. Still something we need to look out for. So the first derivative will be 4/3 x minus 1 to the power of 1/3. And then when we differentiate that again, okay, we multiply by the third, in which case we get 4/9. Drop the third by 1, in which case we get minus 2/3. And then basically, because the question was written in the way it was, we want to put our answer back into that form. Okay, so it becomes something along the lines of 4 over 9 times by the cube root of x minus 1 squared. Okay, right. The context we use this in, so this is more likely to be the question, I'd imagine. Okay, we can actually determine the nature of stationary points through this. Okay, so in higher, you obviously use the table. It's a bit of a faff. I know a lot of you like doing it, but it is a bit of a faff at the end of the day. So we can actually use the second derivative to help us determine the nature of the stationary points, to save us the kind of falderal of using the nature table. Okay, so in a situation where we find that our d squared y over dx squared is greater than 0, so obviously by this point we've substituted something in, so we know at this point where the stationary point occurs, okay, from what we've done with the first derivative. If we substitute that value into the second derivative and our answer is greater than 0, then the stationary point is a minimum stationary point. And likewise, if we substitute in and we get our d squared y by dx squared less than 0, then the stationary point is a maximum. Okay. In the unique situation where d squared y by dx squared is equal to 0, the second derivative may indicate a point of inflection, and so a nature table will need to be used to confirm this. Okay, so just look out for that one, but it's more likely to be one of the first two. And from now on, you can use this instead of doing a nature table. You don't have to go through that whole process. Okay, so in terms of an example like this, we're going to find the stationary points on the curve when y equals x cubed minus 3x squared minus 9x plus 11 and determine their nature. Okay, so virtually a higher question, and in fact, in an advanced higher, they might say and determine the nature by the second derivative. Okay, so but either way, you're probably better off using the second derivative from now on. Okay, so starting with our function, first thing we're obviously going to do is differentiate. Okay, so all I've done is I've just written that, so we're finding the derivative of the first function. You don't have to write it like that. I'm not quite sure why I've done that. in which case we get 3x squared minus 6x minus 9, okay? So the first thing we actually have to do is find where the stationary points occur. So remember, when we've got the derivative, the stationary points occur when dy by dx equals 0. So in this case, when 3x squared minus 6x minus 9 equals 0. And then it's just a case of factorizing that. You can take out 3 as a common factor and just get rid of it. And then you factorize what's in the brackets. Right? Don't make the stupid mistake. Don't say 3 equals 0 or anything ridiculous like that. Either x minus 3 equals 0 or x plus 1 equals 0, in which case x equals 3 and x equals minus 1. Okay, so we've got two stationary points. We just don't know the nature of them yet. So if we take the second derivative, okay, and again, you don't need to write this. This is just explaining it. The second derivative is the derivative of the first derivative. Was the first derivative differentiated with respect to x is what I'm trying to say there. In which case, it's that differentiated with respect to x, which just gives us 6x minus 6. So that in itself doesn't tell us much, but now that we know where the stationary points occur, we can substitute those values in. So when x equals 3, so when we know there's a stationary point, we substitute into here, we get 18 minus 6, which is 12, which in itself is greater than 0, in which case the stationary point that occurs when x equals 3 is a minimum stationary point. And when we substitute in minus 1, okay, we get minus 6 minus another 6, which is minus 12, which in itself is less than 0, which case it indicates a maximum stationary point, okay? Right. Mistake I think most commonly made is this at this point is just leave it, but we've not found the coordinates. So what we actually need to go on is what we need to do is go on and find where what y equals when x equals 3 and minus 1. Okay, so obviously substituting back into the first one. So it's important to know what all of these different equations mean. Now we've got 3 of them. Okay, we need to know what each one of them means. The second derivative is determining whether it's maximum or minimum. The first derivative is determining the gradient at a certain point. In which case, for stationary points when the gradient is 0, and then the first one is telling us all the values of the points on that graph. Okay, so we've got a point when x equals 3, we substitute into that one, and we work out that y is minus 16, and when x equals minus 1, z equals 16, and then it's just a case of nice and clearly writing your answer. Okay, so the curve y equals x cubed minus 3x squared minus 9x plus 11 has a maximum stationary point at minus 1, 16, and a minimum stationary point at 3, 16. There's a minus missing there. That should be minus 16. Okay.